Hello, everyone. Come on in. Come on in, everybody. Anybody have any questions before we get started? All right, I'm going to fill out my notebook page so it'll be named properly. But feel free to speak up and ask me any questions if you have any. All right, coming on in. So that's all made, easy peasy. Got this. Now it looks like everything's working. Got a fly that's found me. That's nice. I don't know where he came from. Jerk. I'm assuming y'all can actually hear me. Somebody chat whether they can, or if that's
you. I can hear you.
Okay, cool.
Yeah, I got a question for you,
Matt.
Mr. Younger. So, a couple things. I'm currently in physics right now, and we're covering basically the same kind of stuff, at least I have in the past two classes, with unit vectors and such forth. Are we going to be doing a similar concept using 3D structure and like statics with unit vectors and stuff like that? Because unfortunately, the professor I have is very, we'll say, textbook. So the concept is kind of slightly lost to me.
Gotcha. Yeah, we will cover that. That's actually chapter 3. We start covering vectors. We're finishing up chapter 2 today, and we do use unit vectors. For instance, we use IJ and K, but I actually in the 202 or the 242 sequence, I actually use IJK. I use R hat, theta hat, phi hat, rho hat, all the different unit vectors, even from spherical coordinates and cylindrical coordinates. And stuff like that. So yeah, I definitely cover all that. So you'll be jumping into it pretty soon. Hopefully, it'll augment your class.
Yeah, it's we're already in it, but more the concern or question, at least for me, was the sake of how many variables there are in play and trying to, name and date or to each variable to what they represent.
Gotcha.
It just wasn't explained well enough, in my opinion, by him. So I didn't know if you were going to go over it.
Hopefully my class will help you. Are you in statics or are you in dynamics or neither?
Statics.
Okay. Yeah, I've been through the statics dynamic sequence in NC State as well. So I have some knowledge in there. I know about couples and moment diagrams and shear diagrams and bending, which actually that normally comes around in strength materials where you have to do a third order differential equation to find the actual bending. But that kind of stuff I can help you with. If you have any specific questions, you can ask me during class. This fly is awesome. I'm just really excited about having this fly in the house with me. It's almost like that bag of clothes should be back there. Shouldn't be. It's probably helping.
Well, it's like the concept of the trig and the differentials is, we've all gone over that stuff since 6th grade, but it's just a lot of the applications are kind of foggy.
Yeah, and they do a lot of quick stuff. They use similar triangles a lot. So, they'll have these obscure similar triangles, not just 3, 4, 5, like 11, 12, 13, or some weird stuff like that. And they'll just, throw that out there and you're like, oh, okay. So that's 11/13 is what the sine of that angle is. So that gets a little confusing. And then, like I said, they do things quite differently from the way we do in physics. They really try to take the creative aspect out of it, which we try to keep in, so that when you're confronted with a type of problem you have to solve, you've got a set algorithm you can use to work through that. Whereas we sort of sometimes I would like to give people an algorithm, but I know you're going to face problems where you don't have that algorithm and that algorithm doesn't work. So I want you more prepared to be on the creative side and just come up with a way to do it. So yeah, but I can help as much as I can, as much as obviously that was a long time ago when I took my statics class, but that's ultimately what part of my YouTube channel is supposed to include is statics and dynamics. I even brought home my engineering books. There's a book called Briar that's sort of the Bible of wooden structures. So if you want to know how to build a house, whether it be in an earthquake or hurricane prone area, that'll tell you. It tells you, you know, how to spec the individual members of a floor beam or a ceiling joist or a roof rafter. It tells you, you know, cladding and strength of materials, and it even comes, like when I bought that book, it came with the National Forest Products. I guess it's sort of 5 annually manual where they put out the actual strengths of the various types of wood, spruce, pine, fir, #1 pine, #2 pine, southern yellow pine, all that stuff. So hopefully, you know, I can help you somewhat. Anybody else have any questions?
Yeah, I have a question real quick.
Go for it.
So in my lab in mastering, I don't know if you touched on it last meeting or not, but there's 2 physics primers assignments you have listed up here and 2 intro to mastering physics assignments. Do we need to do both sets?
No.
Or is there like,
okay. Yeah, I don't know how 2 got in there. That's not right. Do one, and it doesn't matter which one you do. I'll make sure you get the grade for the right one. Okay. So what I'm going to have to do is I'm going to have to take, and everybody that did 1, I'm going to convert, put their grade in the other column too. And then once I have a column that has everybody's grade in it, then I'll erase the other one. That's why I haven't done it yet, because it's a royal pain in the butt. So it stinks when I have a double one, but you only have to do 1 intro to physics or intro to mastering, and then 1 physics primer, however you want to call that. So yeah, don't worry about doing both of them.
Cool. I just want to make sure.
Thanks. Yeah, I appreciate you asking me that. I keep meaning to tell people, but then again, I've got so many classes going. Sometimes I forget which ones have 2 in it and which ones don't. Anyone else have any questions? Looks like we got a full house. We got 16 folks in here. Stuff's rocking.
Are we meeting on Monday? Because Monday is the Labor Day. Are we meeting on that day?
No, day off for you guys, but you do have a test due, so make sure you knock that out. Test 1 on chapters 1 and 2. It's an online test, so you get all those, you know, freebies. You get Google, you get your notes, you get your textbook, you get any other book you want. Like I said, you can literally Google solutions if you want. The main thing is don't run over the time, and don't get help directly from a person. Okay. And that means directly or indirectly. So, you know, you can't get help from a person by texting them, by speaking to them face to face, by emailing them, or by that person having just taken one of my tests, that test specifically, and then posting that online some way, and then you look at those answers. That would be another form of cheating. Can I predict you doing that, or can I detect that you're doing that? No, but that would be, you know, just dishonest and unfair. But other than that, everything's free to do. Just like I said, I just want you guys to have a chance to make a good grade. If you have 1 or 2 questions that you sort of can't remember, it would be nice for you to have enough time to look it up, because that's, again, another learning experience. And that's also why the tests don't count that much, because they're, you know, I don't even know if you're taking them, to be honest with you. I can't even tell that. So the midterm and the final are the major grades.
Thank you.
No problem. All right, so we got another person coming in. Now we got 17 people in here. So last time we spoke, I derived for a constant acceleration the kinematic equations. I defined that average speed is distance divided by time. I sort of hinted at the velocity, the average velocity being the displacement vector divided by time, because velocity starts with v, and it's the vector quantity, which also starts with v. And speed is a scalar quantity, and both speed and scalar start with an S, so you know they're alike. The main difference is a lot of people will say the speed is the magnitude of the velocity, and that's true a lot of the times. But when you do something like calculate the speed or the average speed versus the average velocity of a T-baller that hit a home run, the average velocity is likely to give you 0, because the displacement vector is this vector that points from whatever you call the origin of your coordinate system to where the batter is. So if the batter hits the ball and touches home plate, at that instant in time, that's this displacement vector, is a vector that comes from the origin and goes to the home plate. Now the little kid's going to run to first, which might be 60 feet in that league, and then 60 feet to second, and then 60 feet to third, and then 60 feet back to home plate. And now the final displacement vector is the exact same thing as the initial displacement vector. So the displacement is 0, and therefore the average velocity is 0. Whereas the average speed would be 4 times 60, which is 240 feet, divided by, let's say, 40 seconds. Okay. That 40 seconds is then 60 feet per second. Okay, that's obviously way too fast, but that's the point. Okay, so other than those weird scenarios, speed can be the magnitude of velocity. So we then went from average velocity to instantaneous velocity, and that was defined as the derivative of the position vector or the displacement vector with respect to time. And then we talked about an average acceleration, which is the change in velocity divided by the change in time. If we actually use constant acceleration, however, then that's the very definition of acceleration, and you don't have to do any more. But if you want to talk about the instantaneous acceleration, then you got to take the limit as the time interval gets infinitesimal, just like we did with the velocity, instantaneous velocity, taking the time interval as it gets infinitesimally small. The dx dt is that happening. So similarly, you get acceleration as dv dt. And then from that, I was able to derive the kinematic equation. So I took A being a constant, I integrated A equals dv dt. I got V of t equals V0 plus AT. And then I said, well, V of t is actually dx dt. So then I integrated that again. That gave me 1/2 AT squared plus V0t plus x0. And then finally, I was able to solve that V of t equals V0 plus AT, solve that for t, plug it in the x equals 1/2 AT squared plus V0t plus t0 plus x0 equation. And from that, I got V squared is equal to V0 squared plus 2a parenthesis x minus x0. So that's me verbally telling you the kinematic equations that I derived last time. I also told you that if the acceleration is a constant, you can also use this other equation, which is the initial velocity plus the final velocity. And it doesn't even have to be the initial, it'd just be the velocity at one point plus the velocity at some other point later, divided by 2 is the average velocity if the acceleration is constant. So all those things are true for a constant acceleration. That being said, I then derived the kinematic equations for an acceleration that was, say, linear in time, like a is equal to 2t plus 3. I set that equal to dv dt, integrated it, solved for v of t, set that equal to dx dt, integrated it, and got more equations. So that's really all we've done so far in chapter 2. Chapter 2, however, also includes something called Galilean Relativity. Feel free to ask me any questions. I'm just on a roll right now, so just interrupt me or do your little hand up thing on the participants page, and that'll help me see it. But we didn't talk about what we call Galilean Relativity. So there's no coordinate system that the whole world has agreed upon to use when we're solving physics problems. And because of that, your coordinate might be moving with respect to my coordinate. And you say, well, nah, we'll just make it all relative to the Earth. But then I'm going to have to tell you that the Earth moves on the order of a couple thousand miles every second. And that's as a result of orbiting the sun. Not only that, at the equator, you're several hundred miles per hour moving just as a result of rotating around the rotation axis of the Earth. And of course, that gets smaller as you get higher and higher latitudes, but still on the order of hundreds of miles per hour. Then you'd say, okay, well, we'll just take it with respect to the sun. Well, that's fine too, but our sun is in fact orbiting on the order of, I think it's 50,000 miles per hour around the center of our galaxy, and it takes about 250 million years to make one loop around that. You say, okay, we'll take it with respect to the Milky Way. Well, the Milky Way is moving too, so on and so forth. So you get very huge velocities, in fact, when you start talking about things in outer space and things in orbit, and even the rotation of a decent planet like ours. Some planets rotate so slowly it's not that big a deal. For instance, the planet Venus actually rotates in the opposite direction we expect, and it goes sort of really, really slow, such that a day is actually longer than a year there. It takes longer for Venus to do one revolution about its axis than it takes to do one orbit around the sun. So that's kind of crazy. When you integrate in physics, what do we do with the C? Okay, the C can come up, but what the C is the fact that when you integrate, you could have had an extra variable that could have been added on there, and we handle that via initial conditions. So for instance, when I did my integration, I said at t equals 0, we're going to agree that the initial position is x0 and the initial velocity is v0. So that actually gave me the ability to not have a C. Had I not given you those pieces of information, then when I integrated dv dt equals a, I would have had to say a times t plus the constant of integration c is equal to v minus v0. And then I could say, okay, well, let's see what v is at time t equals 0. What time t equals 0, v would have to be equal to c. So then you say, oh, well, c is the v0. So that's what happened to that c there. Then you do it second time, you evaluate, you get 1/2 at squared plus v0 t plus c, and that's equal to x of t minus x0. You say, okay, well, when t equals 0, then the x of t is what we want. Well, you see that 1/2 at squared is 0, v0 t is 0. The only thing that left is c, so you see c became the x0. Does that make sense, Mike?
Yes.
So yeah, when we integrate without ranges of integration, then you have to add constants of integration. But in my cases, I always did integral from t equals 0 to plain t, and then I did integral from v equals v0 to v of t. And mathematicians don't like that, by the way. You're not supposed to integrate to the same variable that you're differentiating, that your d is with respect to. That's sort of bad form, but it works for us, so we're okay with that. So when I start talking about this relative velocity thing, I want you to think about a very simple example. Let's talk about, let's say, a Mack truck. So here's a Mack truck's flatbed. And I'm over here somewhere, and I'm watching this thing coming towards me. This Mack truck's moving at 60 miles per hour, okay? And I'm going to say it's moving in what I call my coordinate system's positive x direction. So if I imagine this road being infinitely straight and infinitely level, okay, perfectly level and perfectly straight and infinitely long, so that it can go for a whole hour without changing anything, then I could maybe make a little chalk mark on this part of the flatbed trailer, and then check from the instant I start watching the truck to 1 hour later, check how far that's moved, and I'll walk along and find out, oh crap, I've went 60 miles. That's what 60 miles per hour means. It means that you're going to cover a distance of 60 miles in a single hour. Now, if you imagine, in fact, that there was a dog sitting on that chalk mark at t equals 0, and that dog began to run at 5 miles per hour in the same direction as the truck was going, but doing so on the truck, then if you followed that dog over a whole hour and the trailer was long enough, meaning it's well over 5 miles long, okay, what you would find is that in that same hour where the chalk mark on the truck went 60 miles, the dog would have left that chalk mark and traveled a distance of 5 miles on the back of the trailer. So what you'd see is basically this chalk mark covering a distance of 60 miles in 1 hour, whereas the dog did all that plus an extra 5 miles at the end. Therefore, the dog has traveled at 65 miles per hour. Okay, that is the Galilean relativity. And the easiest way I found to make a formula for that is one that we use in relativity. And I'm going to share it with you now. First, I'll share it in Galilean form, and then I'll share it in special relativity form. And I'll work a problem both ways. So what I'm going to do is share my screen with you. And it just worked, so hopefully it'll continue to work, but I can't promise anything. You know how stuff is here. Yes, it's working. It's a good day, everybody. Mr. Younger's very happy. So what I've found to be helpful is, let's say we want to know the velocity of the dog with respect to the road. Notice how I said that and how I wrote that. The velocity of the dog, so that's the first subscript, with respect to the road, so that's measured by me standing on the side of the road, is equal to, and I don't know what it's equal to, but I can tell you some cool rules. I'm going to take this first one and make its first subscript into D. I'll leave a space for its second subscript. And then I'll take this velocity and I'll leave a space for its first subscript, but I'm going to make it second subscript R. Because the important thing is these two subscripts have to match the outer two subscripts. Oh, I don't know what just happened. So that's rule one for how velocities add in relative coordinate systems. The other rule is whatever I choose, let's say I say T for truck, whatever I choose there, I have to choose here as well so that these inner two ones match. Okay. So that works. And in fact, it doesn't just work in one dimension, it works in 3 dimensions. So I can put the vector symbol over top of it, which will make more sense of next week. But right now, just know that vectors are things with magnitude and direction, and this works for those as well. Okay. So we've got that. Now, what I know was I said the velocity of the dog with respect to the truck was equal to 5 miles per hour. And the velocity of the truck with respect to the road was 60 miles per hour. So this formula, in fact, gives you 5 miles per hour plus 60 miles per hour. So it seems to match our reasoning that got us the same answer, 65 miles per hour. So this can be, for instance, the velocity of a boat with respect to the bank when you have the velocity of the boat with respect to the water and the velocity of the water with respect to the bank. Okay. Now, the third rule for this is that VAB, for any arbitrary A and B, is equal to the negative of VBA. So what I mean by that is if you need to flip the indices, the subscripts, change the order of them, all you have to do is change the order and replace the symbol in front of it with a minus. So if it's a positive, you're going to change it to a negative. If it's a negative, you're going to change it to a positive. So that's the 3 rules about addition of velocities. So let's take as an example that ugly Earth. Now, I really thought my program was going to come to my rescue, but no, my program did not come to my rescue because it's a pump. There you go. That time I did it. So this is Earth. And us on Earth have decided that the coordinate system is such that X points to the right. So I'm going to say X points to the right. And here's aircraft A. And aircraft A is moving at 3/4 of the speed of light. That's what we call velocity of A as seen by Earth. Now over here is spacecraft B. It's moving with a speed of -7/8 c, and we're going to call that the velocity of B with respect to Earth. Okay, I had to call that negative because everybody, vehicle A, vehicle B, and us on Earth all have to agree which direction is the positive direction to do this. Okay, now that we have that, I can ask you, what is the velocity of B as seen by A? Well, all you need to do with this is follow our rule. So I'm going to write velocity of B as seen by A is equal to, I know my outer indices have to match, so I'm going to say VB space plus V space A. So that has to be the case. I see that I have a VBE up there, so I can put the E here, but that's going to require this to be E right here. And we don't have that. We have VAE, not VEA. So that's where rule number 3 came in. I can say this is the same thing as the velocity of B as seen by E minus the velocity of A as seen by E. Does that make sense? All right, let me let Eric in. Now that I have that, I can write this as, I'm going to try to cordon off this area. Okay, so the velocity of B as seen by E is -7/8 c. I guess I just changed the pen color, so we're going to keep it that way. And now I'm going to say minus VAE, which is 3/4 c. And you see that makes sense. It actually gave us what we expected. The magnitudes of these velocities should add together to give us a new velocity. But this, in fact, did more than that. It made it so that those two magnitudes added together, but it also made it so that it came out negative. So we realized that, yeah, craft A thinks craft B is moving in the negative X direction. So 3/4 becomes 6/8. 6/8 plus 7/8 is as if they were the same sign, which they are. 6/8 plus 7/8 is 13/8. The speed of light. Well, that's what you get with Galilean relativity. The speed of light can be exceeded. However, Einstein, when he looked at the equations of electricity and magnetism, he realized that they were telling us the speed of light is a constant, independent of the motion of the source and independent of the motion of the observer. So he had to look for some way that was consistent with that, but to add velocities. So it turns out this formula right here is correct as long as you're not dealing with speeds anywhere close to the speed of light. Okay. And this part's correct as well. But if you wish to know what Einstein's equation was, then you'd have to say VAC is equal to VAB plus VBC. So that's just like the other part, but it has a denominator that's 1 plus VAB VBC over the square of the speed of light. So that's the only difference between relativity and Galilean relativity. So what I'm going to do now is work that same problem just for fun, okay? It's not something I'm going to require you to do yet. We'll have plenty of time to do this problem later, But right now, I'm just going to show you what the answer is in terms when I actually do it correctly. So the velocity of B as seen by A should actually be equal to negative 13/8 C divided by 1. Now, remember, we had to switch the A or the EA to AE. So this is going to become a negative right here instead of a plus like I have up there. So now I'm going to say VBE, which is negative 7/8 C. And then I have VAE, which of course is 3/4 C. And then that's all divided by C squared. So you can see this C will cancel out with that C and that C. And I'm going to get negative 13/8 C over. Now, when you multiply, notice the negative and the negative will make a positive out of that. So when you multiply 7 times 3, you'll get 21. And then when you multiply 8 times 4, you're going to get 24. Or excuse me, 32. I don't know what I was thinking of that. Now, 1 is the same thing as 32 30-seconds. So I can also write this as negative 13 over 8. And now I'm going to take and say 32 30-seconds plus 21 30-seconds is equal to 53 30-seconds. So that's in the denominator. So I'm going to write it upside down and say 32 over 53, and then the C is still over there. Now, this is 8 times 4. So that 8 will cancel out with this 8. And ultimately, I get negative 4 times 13, which would be 52. So it's negative 52 over 53 C. So notice it does not exceed the speed of light, which is one of the rules of relativity. Once you take the two postulates of relativity, it basically says only light and other massless things travel at the speed of light. And it doesn't offer any idea that anything can exceed the speed of light. And that's what's happening here is, yeah, I got a lot closer to the speed of light as the relative velocity of A to B, but it's still not greater than the speed of light. Any questions on that? So that second relativity part was sort of for fun. Like I said, we'll get more experience with it later. But the types of problems you're going to be solving in chapter 2 are stuff like an airplane is headed due north at 300 knots, but it's flying in a wind that is coming out of the west at 30 knots. So they want to ask you, what's the velocity of the plane relative to Earth? Well, that's the velocity of the plane relative to Earth is equal to the velocity of the plane relative to the air plus the velocity of the air relative to Earth, so that all the little indices or subscripts match. That's all you got to do. Okay. If they happen to be, like in this case, the velocity of the boat, or excuse me, of the plane was due north, and the velocity of the wind was to the right, then they're just going to add like Pythagorean wise. So you have a 300 leg and a 30 leg, and what you're wanting to find is the hypotenuse. So you're going to take 30 squared and 300 squared, add them, take the square root, and you'll get the magnitude. Then you can use the inverse tangent to find the angle. So does that make sense to everyone? I know I'm sort of highbrow on it, but the main thing is you've seen an example. You'll see examples in your book, but that's the difference between Galilean relativity and special relativity, is that little denominator in the special relativity formula. By the way, this relativity equation, the special relativity one that's written in blue but boxed in red, that's only for one dimension. So it actually gets quite complicated if you're trying to talk about the various dimensions. So I would not put vector symbols on that formula like I did with the Galilean relativity one. Okay. All right. So we're going to move on to another problem. And the problem I'm going to do here is I'm going to stop sharing real quick, and then I'm going to share my screen with my browser that happens to have the textbook open. Here it is. So let's look at number 1. I think that's the problem I'm looking at. It says if you're driving at 85 kilometers per hour along a straight road and you look to the side for 2.0 seconds, how far do you travel during this inattentive period? So when you're first starting off in physics, what you got to learn is what symbols correspond to what. And then you try to learn all the equations you have relating symbols to other symbols. And a lot of your physics initially is you trying to figure out which one of the equations has the symbols that I want and the symbols that I have, but not the symbols that I don't have or don't want. Sometimes you'll find that, but not always. Sometimes you'll have to solve for something you don't want and then plug that into another equation that has the thing you do want. And that's perfectly fine. That's a 2-step, more college-like level physics problem. Hold on a second, people. I need to, this is my daughter's friend. I want to make sure everything's okay. Hello?
Hello?
Hey, is everything okay?
Yeah, I just thought my phone's like dead, so.
Okay, I'm in a class, and but the front door is open if you're coming home.
All right, thank you.
Okay, love you. Bye. Sorry, everybody. My daughter was using someone else's phone, so I was afraid something happened. Anyway, she should be here in a minute, so be prepared to hear a ferocious 6 pounds of Chewbacca-looking Chihuahua raising heck when she gets here. So a lot of physics really is about, hey, what equations got the symbols that I want, and knowing what the symbols are, and also reading to find out things that they're giving you hints to but aren't openly telling you. There's not a lot of hints in this one, but I will tell you that for number 1, I'm writing it down on my pad and I'm getting ready to switch to the pad. Number 1, what I found is that 85 kilometers, that's a velocity because it's in units of kilometers, which is distance, divided by hours, which is time. So that's like distance per time. So I know that is a velocity, and it happens to be 85 kilometers per hour. And then time is 2.0 seconds. Okay, so that's what I'm recording here. But they want to know how far will the car travel during that time. So that's going to be my displacement, which I either call x or x minus x0 or delta x. I'm going to call it delta x equals question mark. So now that I have that, I'm going to stop sharing, and then I'm going to start sharing this way again. Okay, so that's what I've written down. Now, what we know from one of our formulas is that average velocity, which I'll just mark with a bar over it. Sometimes I might also mark it like this. Both of those mean it, or I might just say V average like that, is equal to delta x over delta t, which you can also call it distance divided by time. It's fine, whatever. The main thing is when we know this, then we can see that delta x is actually just equal to V times delta t. And since we're not told this velocity is changing or anything, we don't even have to specify that it's average. It's just going to be the velocity that we have. Now, I've got the time in seconds, but I've got the velocity in miles per hour. So I either got to convert the seconds to hours, or I got to convert the kilometers per hour to kilometers per second. What I'm going to do is I'm actually going to convert the kilometers per hour to meters per second. And the way we do that is we'll say V equals 85 kilometers over 1 hour. And I'm going to say that 1 hour is equal to 3,600 seconds. And then I'm going to say that 1 kilometer is equal to 1,000 meters. So you see, I'm ultimately just dividing this answer, this 85, by 3.6. So I'll say 85 divided by 3.6, and I get 23.61 meters per second. Now I carry 2 extra sig figs there. So now I can say delta x, the distance traveled during that 2 seconds, is 23.61 meters per second times 2.0 seconds, which gives me 47.22 meters, again with 2 extra sig figs. Okay, that's almost 50 meters. That's probably pretty close to 50 yards, in other words. So when you pay attention or stop paying attention for even a brief interval while driving at, a speed like 85 kilometers per hour, you are actually covering a lot of territory. That could be, that could be a whole line. That could be a whole class of kids all lined up you could have been run into if you hadn't paid attention. So that's why we don't want you texting while driving and stuff like that. What I recommend, and I'm being sarcastic here, I recommend that you just do long division while driving, because that's what I do. Is I constantly divide my miles by hours to get my average speed, or divide my miles by gallons to get my miles per gallon. I'm a horrible driver because of that, because I'm constantly doing math in my head. It's just driving seems a little boring. So anyways, but that's a simple problem. Does that make sense? Anybody have any questions on that? Okay, so now let's check another one.
Why the extra signet figures.
Oh, so that was actually me keeping extra sig figs. It's best whenever you're solving a problem to keep extra sig figs all along the way, at least 1 extra digit. And then finally, when you go to say turn it into the homework system, you round it appropriately. So you go back and see where you rounded before, or where you should have rounded before, and then figure out where you should have rounded, and then ultimately where you should have rounded at the end, and then put your answer in. That way, you'll be doing more like what the actual solution writers did, because that's the way we do it. Is we work all the problems to the very end, then we plug all the numbers in, and then use sig fig rules to do that. So I like to keep just 1 extra.
If we do like the test or something, I know Pearson's kind of relentless when it comes to accuracy and precision. Do you check over it? If we say we put in exactly 47.22 when it should have been 47, do you take that into account, or is it just based off?
Yeah, I've set it where I think it allows you plus or minus 2%, and then other settings in my lab and mastering are set such that you can have a difference of like 3 in the last decimal point. So if you turn in 25.3, if the answer is 25.6, it'll accept it. If the answer was 25.7, it'll say, no, that's too far. So that's what I do with my lab and mastering, is I try to turn the sig figs off by either allowing a variance in the answer of a few percent, or by allowing an answer to vary by several digits in the last digit. So it should be meaningful. If you find one where you think it's just purely a sig fig thing, take a screenshot of it, or record the actual problem number that it is in my lab and mastering, and in what homework assignment. Send that to me, and I will check it individually. If I find that it just had a sig fig error, then I'll probably give it to you, unless you were just god awful at the sig figs. Like if you gave 12 decimal places when you're only supposed to have 3 sig figs, yeah, I'm not going to give you credit for that. Does that make sense, Mike? I thought that was Mike. Maybe it wasn't. All right. Well, I guess I handled that. So let's look now. When you're looking at the problems at the end of a chapter, you will see that some of them have 1s next to them. That means they're really a lowest level problem, not very difficult. Once they move up to 2s, they get a little harder. And 3s are, of course, really hard ones. And then there's some other terminology they use. I think there was something like it has a computer or something. In that case, they're actually expecting you to use like a computer using Excel or write a computer code or something like that. I don't think any of them have it in this, but you can see what they are. So what I decided to do was number 5 here, and I'm going to write down what number 5 gives me and state the symbols that it's given me. And then I will share my tablet screen so you can see it, but I want to talk you through it. It says number 5, you are driving home from a school steadily at 95 kilometers per hour for 210 kilometers. It then begins to rain and you slow to 65 kilometers per hour. You arrive at your home after driving 4.5 hours. A, how far is your hometown from school? And B, what was your average speed? So what I'm going to write off immediately is that V1, since there's obviously a couple velocities, I'm going to say V1 is one of the constant velocities. So constant velocity and average velocity mean the same thing. And that is, in fact, 95 kilometers per hour. And that is done for a distance of delta x1. So that's what I'm saying I'm using for the 210 kilometers. And then it says velocity 2 is 65 kilometers per hour. So I'm calling that V2 65 kilometers per hour. And in this case, it doesn't give you any other details about that leg of the trip, but it does say that you arrive home after 4.5 hours, which means T total, and that's what I'm going to call it, T subscripted total, is equal to 4.5 hours. Part A, they would like to know delta X total. So I'll write delta X total equals question mark. And then part B, they want to know V average total. I could call that whole trip or whatever. Okay. So that's the symbols I've given everything. Now I'm going to let you see them. So let's read it one more time so it's fresh in our mind. You're driving to your home from school. For the first 210 kilometers, you drive at 95 kilometers per hour. Then it starts to rain. So you slow down to 65 kilometers per hour. But the whole trip takes you 4.5 hours total. So how far away is your home? And B, what's your average speed? So I'm going to stop sharing here. I'm going to start sharing again with my iPad. And now I got to do this and this. Oh, great. Now all of a sudden it says it can't connect. Urgh. Okay, hold on a second. This will take a second. What I got to do is go to my settings. I'm going to turn off my Wi-Fi on my iPad. Now I'm going to turn it right back on. It's now connected to my, it's working on connecting to my router. Okay, I'm now there. Now I'm going to go back to GoodNotes and I'm going to try to share screen again. It ran away from me. Nope, it says unable to connect because it's a but. So let's stop sharing for a second. Let's see again. I'm going to try to kill my Wi-Fi. And now I'm going to try to turn my Wi-Fi back on. Second chance, the second time's a charm, maybe, hopefully, I don't know. And now I'm going to go back to GoodNotes. I'm going to try to share again. Share. Now I'm going to try to pull up the screen. Yes, it worked this time. Okay. I don't know why it keeps doing that, but that's the nature of it. So we're back. Now, you see what I wrote. V1 was 95 kilometers per hour. Delta X1 was 210. V2 was 65 kilometers per hour. The total time was 4.5 hours. What we'd like to know is the total distance. And then we want to calculate the total average speed over the entire trip. So what we're going to use predominantly is that V average is equal to delta X over delta T. Okay. Again, I'm just writing a different way by putting that bar over it. If I use V1 and delta X1, I can find T or delta T1. So delta T1, meaning the time that he rode before he hit the rain, or you rode before you hit the rain, whoever it is, that is going to be equal to delta X1 over V1. Now, since V1's a constant, that's what they're telling us anyways, we don't have to write the average there. We just know what it is. Now, in principle, you could, and this is what I did with my class this morning that I met face-to-face, is I can go ahead and just convert, 95 kilometers per hour to meters per second by dividing by 3.6. And then I can convert that delta X to just plain meters. And then I can convert that time to just plain seconds. And I can do the same thing with the 65 kilometers. But you can also do it as is, as long as you watch your units. So I'm going to do it as is this time. So my students will watch this. We'll get a little heads up as well. And you get to see another part because I told you about the other way. So the delta X1 is going to be 210 kilometers. And you're going to divide that by 95 kilometers per hour. Now, I was doing this in my head and I realized it should go basically twice, and then you'll have 20 left over. So it'll be 20 95ths. When I started to divide 20 by 95, I ended up getting like 0.21. So I think it's going to be about 2.21 doing it in my head. But let me go ahead and do 210 divided by 95 kilometers per hour. That gives me 2.21053. And that turns out to be just plain hours. And notice I have, in fact, 2 extra sig figs that I carried there, the 2 ones. It's actually 1058, but I had to round that to 1. All right, so that's how many hours the first leg of the trip took. That now allows me to figure out how far the second leg of the trip was in time, because all I have to do is take away 2.2 from 4.5, and that'll tell me the time traveled at 65 kilometers per hour. So delta T1 is going to be equal to 4.5 hours minus 2.211 hours. Again, realizing that the 1s are extra. I get 2.289. So I'm going to say this is 2.289, which really we're just going to call it 2.3 if that was an answer. But that actually turns out in hours with 2 sig figs. So now that I know delta T1, I can use that with V bar equals delta X over delta T to find how far we traveled at 65 kilometers per hour. So again, V bar equals delta X over delta T gives me that delta X2, and actually, yeah, I said 1 there. That should have been a T2. I just corrected that. Everybody see I changed that to delta T2. That's really what I was supposed to call it. I don't know why I called it T1. We already established T1 was, our 1 was the 95 kilometers and all that stuff. So what we can see is delta X2 is going to be equal to V2 delta T2. So V2 is in fact 65 kilometers per hour. And I'm going to multiply that by 2.289 hours. Notice how the hours just cancel out with the hours in the bottom and give us kilometers. So this is what I mean by the units are working. Just like when I divided 210 kilometers by 95 kilometers per hour, from a mathematical standpoint, what happens is that kilometer is going to be multiplied by the reciprocal of kilometers per hour. So that's hours per kilometer. So the kilometer in the top, from the top, cancels out with the kilometer that's now in the bottom from taking the reciprocal of the bottom one and just leaves the hour on top. So all the units are working out. That's how I know it's okay. If you got somewhere where units weren't canceling out right, you'd have to, reach some decision on what common unit you want to use for at least some part of it. So I'm going to multiply 65 kilometers per hour times that 2.289 whatever unit, and that gives me roughly 148.8 kilometers. Okay, again, that's 2 extra sig figs. So I now know that the answer to part A, delta X total, is equal to 210 kilometers plus 148.8 kilometers. And really, I should only be carrying this to 2 sig figs. So I'm going to say 148 plus 210 gives me 359. It's 358.8 kilometers. So obviously you would call this 360 kilometers is how far you live from school. So if you put it in MyLab and mastering, you could call that 3.6 times 10 to the 2. That's the way you specify a 2 sig fig number that is in the order of 100. You'd have to say 3.6 times 10 to the 2. So that's part, I don't know why I wrote that last part. That's supposed to be part A, and I seem to have written a 6 in there for some reason. So there's A. Now part B is what is the average velocity total. Well, remember that V average is always delta X over delta T. So we now know the distance was 358.8. Here I am carrying an extra sig fig. And then I'm going to divide that by the total time, which is 4.5 hours. So this actually gives it back to me in kilometers per hour. So that's super helpful. So I'm going to say 358 divided by 4.5, and that gives me 79.7 kilometers per hour. And that's my answer to B. Any questions on that? All right, so that's just some use of the kinematic equations. Another one, and there's plenty of examples in the book. You'll see plenty of examples that I link to on our Canvas page. For instance, I handle the Tesla S Plaid and learn some things about that, because the Tesla S Plaid can go from 0 to 60 in like 1.2 seconds. I think, if I remember correctly, when I read it, it actually could go as low as 1.0 seconds or something. So that's pretty friggin' awesome. But either way, what we're going to do now is we're going to show you some more examples of using kinematic equations. But this time I'm going to stop by talking to you a little bit about what Galileo did. So yeah, we seem to have about 25 minutes left. So Galileo, after being put in in-house arrest, because basically he interpreted scripture, that was kind of a bad thing. Like a woman had written to him about if the earth actually revolves about the sun, then what did the Old Testament, and she gave the book, it's like Joshua 10:2 or something like that. What do we make of Joshua 10:2 when it said that God made the sun stand still? And literally, he's writing to a noble woman who's asking him this, and he writes back, well, this is one of those cases where we shouldn't take the Bible literally. And then he proceeds to explain that if you actually took it literally, then the effect that God had supposedly done, stopping the sun in the sky, would have actually had the opposite effect and would have sped up the time instead of making it slow down. So you can imagine that would not be cool with the Pope and the Catholic Church in general at a time where Martin Luther's posts and rules about are basically problems about the Catholic Church, and Giordano Bruno's just been burned at the stake, and I'm pretty sure Joan of Arc was recently burned at the stake, that sort of thing. So it was really a sort of a big deal. He was taken to this Inquisition for his book Simplicio, his book that had a guy named Simplicio that represented the position of the church. And that person was holding the idea of a geocentric universe, and they thought the solar system was a universe at that time. And he just said, no, there's no way it's going to be that, and basically made a fool of the Pope, who luckily was his good friend. So they got him to recant. He was quite old by this time. He had went blind, started going blind and everything. And ostensibly, they showed him the tools that they would use to remove his entrails via his gonads with. And him having recently learned of Giordano Bruno, chose not to take that path. So he recanted himself, and they refused to let him teach or write about astronomy anymore. So he said, okay, and they put him in in-house arrest. So he had to stay in the house for the rest of his life. So he went to studying motion, and he did so because he didn't understand how could those Medicean moons, satellites of Jupiter, how could they actually stay up with Jupiter? Why were they not left behind? So he came up with what we now call Newton's first law of motion, but was in fact Galileo's law of inertia. When Newton says, if I have seen further than others, it's only because I stood on the shoulders of giants. Galileo is one of the giants he's referring to. He's also picking on a short man, but we'll get to that later. So anyways, that's what happened. And he tries to study motion, and he drops something, and you see that it falls fast, but he can't tell, does it instantaneously go from 0 to fast and then fall down? Or does it speed up to reach fast? And are those speeds different, like Aristotle had taught, where if you drop, say, a bowling ball and something comparable in size and weight, but not exactly the same in weight, say a field hockey ball, if you drop those simultaneously from a good sized distance, maybe 20 feet or so, you'd see that they do in fact fall at the same rate. That wasn't completely obvious in the time of Aristotle. So if the bowling ball weighed twice as much as the field hockey ball, then Aristotle would claim the bowling ball would fall 2 times faster. So Galileo tried to study that, and he realized that he couldn't see the motion vertically well enough to make anything out. But he reasoned that with trigonometry, if you allowed something to roll down an inclined plane, you could then use a trig function to multiply that acceleration down an inclined plane by a number to get the vertical acceleration. Okay. And it would be going slow enough if the inclined plane was not that steep, it'd go slow enough where he could actually measure it. He even invented a really ingenious timepiece, because time just wasn't that easily measured back then. You can imagine waiting for pendulum flops to go back and forth, or turning over sand capsules, right? So what he ended up doing was he made a time device that was basically a pot of water with a valve, and he'd weigh the pot when it was empty. And then as he started the timer, he would turn the valve open, and then he'd shut the valve when it was closed, and he would weigh the water that filled in there. Well, the amount of water that filled up the trough was directly proportional to the time. So if you got twice as much water in one trial than you did in another, then you had twice as much time. So it's really an ingenious thing. What he discovered, though, was one, he had to come up with some idea about velocity. And he's more or less given credit for creating the idea of velocity and acceleration. And what he reasoned was was that constant velocity was when you take a certain interval of time, say 1 second. And if you find the object moves the same distance every one of those intervals of time, then that's constant velocity. So if I watch and I see a basketball rolling down the hallway in the science building and it covers 2 tiles in 1 second, and then I go down to the far end of the hallway and see that at 1 second it covers 2 tiles again, and then I go just a little bit further and it again covers 2 tiles in 1 second, I could be pretty confident that that thing is at constant velocity. Okay, so velocity really is the change in distance divided by the time taken. He also went further and said, let's see what acceleration is. And acceleration is the change in velocity divided by the time taken for that change in velocity. As we talked about before, the 0 to 60 in 4.0 seconds is 15 miles per hour every second, right? So he even defined a concept of constant acceleration. And what it is if you take a certain interval of time, let's say 1 second, then the object will change speed by the exact same amount every one of those intervals. So for instance, if an object went from 1 meter per second to 3 meters per second in 1 second, then its acceleration should be 2 meters per second every second. So if I check later and measure it for 1 second and it goes from say 7 meters per second to 9 meters per second, then yeah, I'm thinking that the acceleration is a constant, okay? So he came up with the idea of acceleration and velocity and constant acceleration and constant velocity, and he reached the conclusion that 1, objects accelerate when they're falling, which was not what Aristotle taught, and 2, they all accelerate at the same rate, which was not what Aristotle was teaching. Independent of their weight, they accelerate at the same rate. The reason why, of course, you can see a feather would float down like this, but it's a little less obvious when you look at say a golf ball being dropped versus a really large 18-inch kickball, right? You might think it's due to the much larger weight of the kickball, or excuse me, the larger weight of the golf ball, but actually that'd be backwards. But in fact, it's air resistance that's the problem. So in doing that, he did reach that they would all fall at the same rate, and he's right. And we can't understand that yet till we cover Newton's second law of motion. But he said that acceleration basically figured out that the equivalent of it was 9.80 meters per second every second. So if I throw a ball up at, let's say, 19.6 meters per second, gravity pulls downward on it, causing it to accelerate by downward. Since I called up, I'm going to call up positive, I'm going to call down negative. It's going to accelerate by negative 9.8 meters per second every second. So after 1 second, it will have gone from 19.6 meters per second to 9.8 meters per second. And then after 2 seconds, it will go down to 0 meters per second because it again reduced by 9.8 in that second. And then after 3 seconds, it's going to reach a speed of a velocity of negative 9.8 meters per second because the velocity is still changing by negative 9.8 meters per second each second. And then after 4 seconds, it's going to reach negative 19.6 meters per second and be right back at the height I threw it from. Okay. So that was his big discovery. All of the use of kinematic equations is about, at least the way I think of it, is about imagining coordinate systems in space and putting the origin at very specific spots, and then deciding the x-axis in the positive direction points one way and the negative axis points the opposite. Or if you're using the y-axis points one way and the negative y-axis points the other way. And then anything pointing in that positive direction is a positive number, and anything pointing in that negative direction is a negative number. So that's the big trick of using these kinematic equations. So now that I've given you that sort of spiel, if you will, on Galileo and falling bodies, we can now use the kinematics for falling bodies. So I'm going to try to share screen again and hope that it works. No, it does not. That's really super great. I'm glad this is happening. This is making my life so much funner. Okay, so what I'm going to do again is I'm going to shut down my Wi-Fi. Kill it. Okay. And now I'm going to turn my Wi-Fi back on. And now I'm going to do share screen again. And I'm going to do share screen, hit share, and hope it works this time. Yes. Ugh, such a pain in my butt. Okay. So what we've learned is that acceleration due to gravity is a constant, and it is in fact 9.80 meters per second every second. And I'm going to say that's its magnitude, okay, because the directions all depends on our coordinate system. I will also mention that meters per second is equivalent to meters per second squared, but I would prefer you to say it the way I'm saying it. You can write it meters per second squared if you want, that's fine. It might help you mathematically. But when you think of acceleration as meters per second every second, it gives you a little bit more of a feel of what acceleration is. Acceleration is how much the velocity changes every second. So let's keep that in mind. Now, let's solve this problem. Let's say a ball is dropped from a height of 100.0 meters and free falls. Free fall means we're ignoring air resistance. Okay. If it's a bowling ball or something like that, you're probably in a pretty good space for assuming air resistance is negligible. The bowling ball is probably going to make some curves and stuff like that, but it's probably not going to be slowed down an appreciable amount because it's so freaking heavy. But it's going to fall from a height of 100 meters, and it's going to free fall. And we want to know how long will it take to hit the ground that's A, and B, I don't know why I slipped the curve for this, never mind. How fast will it be traveling just before hitting? Okay, so that's the problem. I'm going to write the solution in blue. Now, first off, like I told you before, a lot of physics when you first start it is really reading the problem and sifting information out of it and assigning symbols to it, and also looking for hidden information. So right now I have a big gaudy number of 100 meters. Okay. What I'm going to do is I'm going to assume that my coordinate origin is, say, at the bottom of a cliff, and that we're starting such that x0 is equal to 100.0 meters, and that x final, which is just plain x, is 0. Okay. So by doing that, I have a picture in my head. I don't know why it went to an eraser again. I have a picture in my head, and in fact, the ball falls all the way down here, and evidently the way I've got this drawn This is my positive x-axis. This is 100 meters. And this is my y-axis. And this is my 0 meters. Okay. So by me saying x, the final position is 0, and x0, the initial position is 100 meters, I have, not necessarily on purpose, I have forced upward to be the positive direction. Okay. Since that's the case, then A is equal to negative G, which is equal to negative 9.80 meters per second per second. Okay. That negative has to be there. Once I made those coordinates, that was all you could do. I will tell you that you could have said, let's let x equal 100.0 meters and x0 equal 0 meters. Then that would force A to be positive 9.80 meters per second per second. Both ways would be exactly right. Okay. That's the freedom you have in choosing a coordinate system. You might just need to take the time to draw your coordinate system out. So this is an alternative. We're not doing that one. Okay. Now, what I've got is x0, x, and a, but part A is asking me t. Excuse me. Part A is asking me t equals question mark. Now, do we have any other information? There's some information that's being given here to us that isn't stated as nicely as you might like. Anybody know?
Can we get velocity from the gravity?
Sort of. I think you might be on the right track. Do you know what the initial velocity is?
Your initial and final velocity is 0.
That's a common misconception too. The final velocity, yes, in reality is going to be 0, but we're studying only while it's in motion before it impacts or hits the ground, because that's a force coming in, and forces are going to change things up. Free fall is falling only under the force of gravity. But you are right in the first part that V0 is equal to 0, and that's implied from the word dropped. If someone falls or drops something or releases something, that's code word in the physics world for the initial velocity being 0. Okay. Now, we never study, well, we rarely study when a thing is dropped and then hits the ground. So we're always talking about the velocity, sort of its maximum velocity, the velocity it had the last time before it started slowing down because it was hitting the ground. Okay. So that's actually what we're looking for in part B is V final. So what I was shooting for was this V0 equals 0. Okay. Now I need a kinematic equation that has X, X0, V0, A, and T. And hopefully doesn't have anything else because I can't do anything else. So again, like I said, a lot of physics is about, at least initially, is about sifting information out of the problem and assigning it symbols, and then looking for an equation that covers the things you know and the thing you want to know, but not the stuff you don't know. So in this case, I've come up with the equation X equals 1/2 A T squared plus V0T plus X0. Okay. Now, in order to do that, I've got to, again, think about my coordinate system so that I put the numbers in properly. So what I know is that the final position is 0. So 0 is equal to 1/2 negative 9.80 meters per second every second times T squared plus 0 times t plus 100.0 meters is the x0. Okay, so we're looking out here. Notice that negative 9.8 allows us to take it to the other side and it'll become positive. So I'll get 4.90 meters per second every second times t squared is equal to 100.0 meters. So I can take the and divide both sides by 4.90, and I get t is equal to the plus or minus square root of 100.0 meters over 4.90 meters. Now I'm going to use written as meters over second squared because algebraically, that's a really wonderful thing to see in action, because to divide meters by meters per second to the 2 power, I just flip over the meters per second squared. That becomes second squared per meter times a meter. And I'm going to choose the positive time because negative time makes no sense. So I'm going to say t is equal to positive square root of 100.0 over 4.90 seconds squared. Okay, when I do that calculation, and we're almost out of time, it's 100 divided by 4.9.
4.04. Or sorry, 4.51.
Yeah, you took the square root then? Gotcha. Yeah, I got 20.408 before I took the square root, and you're exactly right. I got 4.52. I just rounded. Actually, I should write that as 4.518 to keep it extra sig fig. This is all 3 sig figs, but that's seconds. And this is actually, that's not even the correct markings of sig figs. That's a extra sig fig, and that's not. So yeah, about 4.52 seconds would be the answer for part A. Now for part B, we want to know the final velocity. So can anybody think of an equation to use for that one? How about that special one that a lot of instructors don't allow people to use, like that? The reason they don't allow them to use it because it's not a vector equation. You're going to see here, for instance, I got to choose a sign for the velocity, right? We've chosen up as positive. So the velocity when it gets to the bottom is downward. So that's got to be negative. So I've already made my choice. I'm going to say v squared is equal to 0 squared plus 2 times negative 9.80 meters per second every second times, now x, remember, is 0 minus 100.0 meters. That's really wonderful because you're not supposed to be getting square roots of negative numbers in a physics class. So this becomes v is equal to the square root of basically 1,960. And notice the units are meters squared per second squared. And I'm going to take the actually, I'm going to take the negative square root because, as we said, the velocity should be downward, which is a negative direction. So v is equal to 44.27. So negative 44.27, carrying 1 extra sig fig, which is really what I did in here as well, meters per second. Notice the square root of meters squared per second squared is, in fact, meters per second. So that's my answer. And I had to make it negative, of course, because it's going downward. And these are actual, vector quantities, velocities, and stuff like that. So does anybody have any questions on that? All right, time is up. We've essentially finished chapter 2 now. So you guys can get your test 1 done. Remember, it's supposed to be done, I think I said by 11:59 Monday night. It might be 11:59 Tuesday night. I'm not sure. But whatever it says on there, make sure you get it done by then. You're allowed 3 chances and only your highest score counts. But I think you're in a good spot to do that. I will pay attention to my email over the weekend in case you guys are taking practice tests and run into any problems. The best way to get help with that is take a screenshot of the actual problem with the various answer choices it has and send it to me and say, you know, I don't understand, or tell me what you don't understand. And I'll do as best I can to get up with you, usually within the same day. Okay. I'll do my best. But other than that, good luck on your first online test, everybody. And I'll wait for the last person to leave before I leave. But thanks for coming. The video should be up tonight.
Have a good night.
You too.
I got a weird philosophical, if you will, question regarding this. Unless you have Joseph, looks like he's popping on to ask a question.
Okay.
Go ahead first.
No, does anybody else have another question that's a little more directly related? I don't mind answering this one either. Do you want me to leave this document open, or do you want me to go ahead and close that? Do you need me to refer to one of the problems we already worked?
Not really.
Okay, so I'm going to stop sharing there. So go for it. What's your question, sir?
Galileo's the Galilean relativity idea. So my question, I'll turn my thing on to, when talking about the concept with using, you said a coordinate plane and no one can get on the same page with regards to where something is because of obvious spherical issues. Have they used like kind of like grid lines? You see them in games and movies all the time where the grid lines shrink to like a topographical relativity to what's around. Have they, I mean, obviously they need to pick a point where 0 is, but have they had that thought process using like take into account the Coriolis effect, take into account topographical maps and location awareness for where they are to see, you know, what 100 miles an hour actually looks like in Antarctica versus here?
Yes, we do that. In fact, you know, there's changes. Even the Earth has a gravitational field that causes relativistic effects, just like the sun does. So we can actually, you know, account for certain irregularities in timing devices, highly precise, you know, like cesium clocks and stuff like that. They show differences in times just by changing latitudes. If the precision of the clock is far enough, that will definitely change it from a speed standpoint as well as a gravitational standpoint. And as far as grid lines go, we actually do have a sort of neat system. If you draw X as the vertical axis, meaning X in space, and then time as the horizontal axis, that's the way we do relativistic diagrams.
And then as you open out, the grids start to slowly enclose. Because
if you draw another coordinate system, then the x-axis will be tilted inward and the t-axis will be tilted inward. And then you have a triangulum, a parallelogram type grid system that you use. And I've actually used that as a way to derive the Lorentz equations. It's kind of neat, but go ahead. What were you saying?
No, so I'm just trying to understand, because obviously like elevation plays a factor and everything else as you move across, but I guess if you can redefine the hold up with everyone for having one singular, because for some reason this spikes my interest, but having one singular rule or definition or equation for deciphering. Like, tell me again, you explained it for a second before we started.
So like what coordinates to use, that sort of thing. So just take a simple case of like my neighbor across the street. This is probably the easiest thing, but it's also the thing you never think about. I watched on here. In fact, one of the videos I have on my YouTube video was this family riding by in a golf cart. And I can actually do mathematics on that with the video tools I have and stuff and figure out how fast they're going, blah, blah, blah. So I do stuff like that. Well, to me, that person went from north to south, and I call that the right hand direction, which is my positive direction. Well, my neighbor, if they happen to be my neighbor across the street, if they happen to look out their window, they're seeing that same golf cart move to the left. They're probably calling that a negative velocity.
So that's the holdup, is what's positive and negative is no one can decipher because no one's on the same page.
That's problem number one. And then, you know, we say up is this way. Well, what happens when you're in the South Pole? Up's now down. So all of that, the geometry of the Earth, everything plays into that. And then ultimately, what Einstein says when he finishes his grand correction of everything, i.e., he submits his general theory of relativity, he says the laws of physics are the same for all observers, meaning what he's now said is no matter what coordinate systems you use, what units of measure you use, how fast you're moving with respect to me and how fast I'm moving with respect to you, we should all agree on the physics. And the only way we can make that happen is to write our equations, what he called covariantly, which was meaning using tensor calculus. So that gives you a reason to say it's okay that we're not all in agreement about what units to use and what coordinates to use, because the laws of physics better be the same no matter what coordinates you're using.
And I guess we're thinking about like Navy ships launching tomahawks or nukes from, you know, Pacific all the way over to, you know, smack London.
Right.
That like South Pacific, like trying to, did they use, I'm assuming I don't know if you know anything about that stuff, but like assuming they use the same kind of tracking and the same kind of physics from one location to the other, there's got to be like an offset of at least like 17 degrees, like in true north and not north.
It's funny you asked me that. I actually have a maneuvering board training manual from the Navy. I used to teach in the Navy ROTC. So at East Carolina and then at Chapel Hill as well. So yeah, I've actually got some of those documents, and yeah, they have corrections to that. Not only that, there's this famous part in Feynman's book where this Navy guy kept coming around and complaining about them making mechanical machines, engineering wise, making mechanical machines that would automatically make projectiles fire on target. And the guy would just come in and ask asinine questions that really aggravated him. So they started ignoring him, which is really kind of rude, but I get it. If he doesn't really understand the process well enough to ask fruitful questions, you sort of just want him to go away so I can do my work. Well, that's the way they got with him, is they were sick of him. And he came in and he asked, what about blah, 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 blah. And they all laughed at him and sent him off. Not really rudely, they just let him go. But Feynman said, and then a couple minutes later, I'm like, holy crap, I've done this whole thing wrong. He was just telling us they were taking coordinates from the aircraft's cockpit, and he asked about them taking coordinates from the projectile's firing spot, which was actually the right ones. They had worked everything out in terms of the cockpit, but not in terms of the turret gunner.
I mean, so in that case, by a matter of 50 or 60 meters, give or take.
Yeah, it could really screw everything up. So in that case, they were like, yeah, we got to be more humble. Even if someone doesn't know anything, that everybody can contribute. And in that case, they learned a lot. And that was kind of cool about Feynman, because he showed himself being an ass, but he also showed himself how he learned from that, and learned that, you know, even people that don't understand what you're doing can offer something helpful on occasion.
Fair enough.
So, but yeah, they got to take into account the Coriolis Force. That's a big deal. It deviates things to the right in the northern hemisphere and to the left in the southern hemisphere. I do know that autopilot, and this is a really weird story, but I know that autopilot doesn't always correct for a Coriolis Force. There was a pilot, a couple pilots and some golf pros flying, I want to say from like Virginia, might have been New York, Connecticut, New Jersey, Maryland, somewhere like that. But they were flying, towards Miami in a private jet.
Mm.
The cabin lost pressure and all of them fell asleep. They got, basically asphyxiated, not dead, but they asphyxiated. And this was shortly after 9/11. So people saw this rogue private jet flying off course and nobody answering. So they scrambled jets from the Navy went out and flew next to them and determined that, in fact, everybody was unconscious. And the crash ended up happening, I want to say, like in Western Texas.
Mm-hmm.
But they were headed towards Miami. The reason that is the Coriolis Force, which isn't a force at all, it's just a matter of the globe rotating under them, turned Miami past it and then turned towards, Georgia, or Florida, Panhandle, Mississippi, Louisiana, Texas, and then he crashed in Texas. So that's an instant where I know that the autopilot did not evidently take into account Coriolis Force, because the autopilot kicked in and didn't do anything.
Yeah. No,
I like people did die.
Yeah, I just like having tangible concepts behind what's up there, which is part of the issue I'm having currently with my statics class.
Yeah. Tangible is helpful.
Yeah, extremely. And it's funny because we were discussing something in class the other day, and he brought up, impossible mathematicians and mathematics regarding, some of the displays of unit vectors and other things like that. And he's like, but that's more advanced math for what's up there. And then I brought up the Coulomb constructor, the 3n+1 rule.
Oh yeah.
And he said, well, that's not what we're talking about.
Yeah, sometimes you get them off course, and that makes it worse because, one, they might not have studied that area and they might make a mistake and look like a fool, and two, they don't want to lose time either, because you got to get through a certain amount of material. So yeah, it can be all sorts of stuff.
Yeah, he was just BSing, but nonetheless, I won't keep you any longer.
No problem.
For the help and everything.
I will tell you that we use something called the Frenet frame in differential geometry. Yeah. And you can sort of take like the space shuttle or an F-18 or whatever, and you can take its keel and make that the x-axis. And then you can create something that's perpendicular to that, and that'll be the y-axis. And then you can create a third thing that's perpendicular to that, and that'll be the z-axis. And if you do it in a certain way, it's called the Frenet frame. And then if you also want to work it out mathematically, you can do something called the Gram-Schmidt process, where you take a vector in 3 space and you subtract that first vector from it and every component like it, and only leave what's left perpendicular. That gets you a second axis, and then you can do it again with a third vector, and that'll give you a third axis, and you get 3 perpendicular axes. Now you've got 3 vectors, and if you divide each of those vectors by its own magnitude, now you've got 3 unit vectors that can be converted to I hat, j hat, and k hat.
Which is still a weird concept that I'm trying to grasp.
Yeah, but that's literally what they do with the space shuttle, is they have to have a coordinate system that's based on the pilots and what they're seeing in the shuttle when it was running. So that's what they do it. And then, of course, that means NASA has to keep the orientation of the shuttle in mind while they're speaking with them. So they have a conversion system back and forth between that.
Keep it all relative to the pilot.
Yep. So that's some hands-on stuff that you could actually picture doing, and maybe it'll help you a little bit understand what the unit vectors are. Whenever you divide a vector by its magnitude, it becomes a unit vector, and it's literally a unit. It's not meters, it's not kilograms, it's not light years. It's literally just a unit.
Fair enough.
All right. Have a good one. I hope that helped.
I did. Thank you.
All right. See you, Matthew. Bye-bye.
See ya. Bye.